Good evening. My name is Scott Norr. I'm an instructor in the electrical engineering department on campus. And I started my engineering career with Minnesota Power in 1986. And I started teaching part-time in the at that time, the electrical and computer engineering department in 1999. And have been teaching at least part-time ever since. And every year I, check my key in the lock, and if it turns, then I'm good for another year. But perhaps some years they'll let me know by changing the locks that my services are no longer required. But when I was asked to talk, I thought I really wanted to talk about some of the potential that we see in the universe that we're not really exploiting. But the more I thought about that, the more I thought that really isn't in the realm of engineering. It's in the realm of science and discovery. And I wanted to be a little more grounded than that in this talk. So we'll still talk a little bit about your place, but we want to talk about what that place looks like. So let's start with a question or a fill in the blank. Pop quiz here. And so we say the quality of life on Earth has been blank by engineers. And I'll give you three choices: harmed, unchanged, or improved. I believe we could all eliminate one of those. Which one would we eliminate? Unchanged. We definitely have had an impact, right? Engineers. How many in this room would say that quality of life, now we're not just talking about infrastructure, saying we've got way more roads and we've got a lot more electrical lighting, but quality of life. Has the quality of life been improved by engineers on the planet? How many of you would say yes? And that's why you're going into this field, right? But it's not without cost, right? So if we think about impact from engineers, every aspect of modern society has been improved in some manner by engineers just like you, sweating the details, double-checking the budgets, and making things work and work better, and incremental improvements on many great ideas. Does anybody have an opinion upon what the greatest modern engineering marvel is? What's either, and that's maybe a speculative question or a open to interpretation as to what great might mean. Anybody want to throw out something that you consider to be a marvelous achievement? Yeah.
Let's go with the mass production of pharmaceuticals and antibiotics. So,
pharmaceuticals, just an explosion of different treatments and therapies available to modern medicine to attack cancer and not quite cure the common cold, but make you feel like you're not going to die if you get one. Anybody else have yeah?
Going to the moon.
Going to the moon, baby. Put footprints on the moon. That's pretty crazy stuff. Anybody else? And there were a bunch of spin-off benefits to that, right? I don't know if I have one, but I have a bias, and we might say that the power grid, which we take for granted, is so great because we take it for granted. When we go to flip on a light, we're surprised if it doesn't actually light, right? We have a high reliability of electricity in this country. That's not true in every country. But the grid that spans much of North America is one of the most complicated machines on Earth. And it's extremely reliable. That takes a lot of engineering. But I'll say some negative things about that too. And again, these engineering advancements have occurred not without negative impact. And I look to the universe to talk to me about that. We have Newton's third law. We push on something, it pushes back. The Chinese philosophy of the yin and yang, the light and the dark. The American philosophy of Republican and Democrat, not so much. If we stand from a European perspective, and maybe Mo will talk a little bit about European perspective, to the rest of the world, I would say it would be a fair statement to say that Democrat and Republican in the U.S. are very close politically and significantly right of center. I think that's a fair statement. So perspective is important, but there is not an engineering achievement that does not have some unintended consequence. Come on in. Come on in. Engineers Without Borders?
Yeah.
Need some ice cream?
Yeah.
And we have to, as engineers, be aware of that there are side effects, or there are ways that our product can be used that are unintended. Any advanced technology in the hands of the right or wrong people could be weaponized, and usually the engineer who brought that technology forward is not aware of the potential for harm from their product. But we should be. We should do everything in our power to think about what is right and what is potentially wrong with what we're doing. And also in this middle paragraph, what resources need to be harvested in order to build our project, and what environmental impacts the gathering of those resources, the manufacturing of our product, and upon the end of its useful life, the recycling of our product should all be part of a significant part of our engineering design. When I look at the future, engineers in the future are faced with two global challenges, and I would say that those are clean water, and I don't know how readable this is. And I'm not any kind of an expert on clean water, other than to know that global demand is rising significantly. The supply of potable water is in decline due to climate change, and that is perhaps the most important aspect in terms of quality of life that we have as a biological being, to have clean water. Something I know a little bit more about is sustainable energy. And let's take a look at energy. These numbers, the number from 2015, the world as a whole, all types of energy, oil, nuclear, electric, whatever, the world as a whole consumed a little over 500 quadrillion BTU of energy in 2015. So a BTU is a British thermal unit, and that is the amount of heat energy it takes to warm 1 pound mass of water by 1 degree Fahrenheit. So not system international units. Of those 516 quadrillion BTU, the U.S. was responsible for 98 out of those 516, of which 14 were electric, and of those 14, 10% of that came from renewable sources in the U.S. So that's the U.S., 330 million people, perhaps 4.5% of the world population, using 19% of world resource. Do you feel like an energy pig? Not necessarily, right? We could dial things back a bit. We could turn off a few more lights. We could turn the thermostat down a little bit. But if we don't if we don't consider our lifestyle gluttonous, we have every expectation that the rest of the world would come to our standard, right? And in 2008, 2009, China also became a 100 quad consumer of energy with something more along the lines of 15% of the world's population. But what if they were consuming energy at the rate that the U.S. was? They would be a 300 quad entity. India also 15% of the world's population. If we brought them up to our standard of energy consumption, they would also be 300 quad. And just those three countries alone then would be 700 quad. And if we add in the rest of the world, maybe if we bring the rest of the world up to our standard, do you see where this is headed? I believe personally that the world right now, we're straining the world's energy resource at present. And to bring everybody else up to the U.S. standard for consumption is definitely not sustainable. And I threw in, I don't know why, but that's a statistic that also makes me wonder some things. But I'm not prepared to talk about those as an engineer. When we talk about the traditional ways, of course I'm an electricity guy. When we talk about the traditional ways of producing electricity, we're talking primarily about coal and nuclear. Those are both heat engine processes. They're bound tightly by the second law of thermodynamics to have an upper bound on the efficiency. And and when we look at in practice, the upper bound might be somewhere in the high 50s or low 60s of %. But if we're burning coal, there are so many things we have to do to reduce the environmental impact of burning coal, where that for every kilowatt hour of energy, electric energy we create, we're burning 3 kilowatt hours worth of coal energy to get that. When we look at that in the big picture on the grid, it looks even worse. So in Minnesota here, we've got a plant in Grand Rapids run by Minnesota Power, our local electric utility. They get their coal from Montana. And let's assume a coal train is a very efficient way to move energy. And it is, I don't know the exact number, but we'll put let's say we mine 100 lumps of coal in the Powder River Basin of Montana, put it on a train. Maybe 1 lump's worth of coal energy is consumed by getting that train into Minnesota. Then I have a generous number on the plant at 38%. And the process of burning coal to produce heat, and heat to produce steam, steam to run a turbine to make a generator spin, and a generator to make electricity, we've got 37 lumps equivalent of electric energy out on the grid. The grid itself, and that was my expertise, computer modeling of what the grid is like now and what it'll be in the future, very efficient. And, I can sit here with these, 98% conversion factors and say, yeah, the grid's great. Electricity is great. It's the mechanical engineers that are letting us down. But so 35 lumps get to our home. Now, if we put those into most appliances, we're going to get between 10 and 30 lumps of that energy for every 100 lumps we burn. But if we use it to make lighting, and we do that lighting with an incandescent bulb, the conversion efficiency is horrible. And we need to mine 100 lumps of coal, burn it, belch the power out the stacks to get 1 lump's worth of energy of light. That's the dirty little secret of the modern grid. And that's why we've had federal regulations phasing out incandescent bulbs in favor of, first of compact fluorescent, but ultimately LED. But at best then, 4 lumps of value for 100 lumps burn. That's just not the way to run a railroad. We got to do better, especially when the byproducts are greenhouse gases and things like mercury and arsenic and other heavy metals in the air that we breathe from burning coal. So what's the alternative? Renewable sources. They're currently 10% of our electric production. They're continuing to rise. The other mega electric utility in Minnesota, Xcel, is investing in another 300 megawatts of wind energy as we speak. And India just became the third largest solar generator on the planet, or by country, with the U.S. and China. And they have this huge Kamuthi plant just went into production. But the problem with renewables is that they're only available when nature allows it, right? Only when the sun shines, only when the wind blows. And ultimately, we want to continue on with our expectation that when we flip a light switch, the lights come on. Ultimately, then we have a storage problem. Our renewables are not, don't listen to us when we say we want them. They only listen to nature. Here's a picture of the electric demand in the state of California. They hit a new peak in 2006, 50 gigawatts of consumption, power consumption. And you can see this is a 24-hour spot, 24-hour window. In the middle of the night, there are 28 gigawatts, rising to 50 gigawatts during the day. That red line being the forecast of what they expected to use, but they were in a nasty heat wave, huge air conditioning load. The grid was extremely stressed that day. Every generator that could produce electricity was on, including a few little hamster cages spinning around, helping out. But for that exact same time window, this red line is the total wind power generation in the state. And California has a lot of wind. And at night, we had quite a bit. I think we had 10 gigawatts of wind. Is that right? Or was that kilowatt? We had 10, was that a K or an M? Anyways, we had a lot of wind. But when we needed it most, the wind was dead calm. So if we could take this energy here where we don't need it as much, run that into some type of storage device, and then release that energy here, that could really help out. But we really don't have anything like that yet. So this is a graph of all energy storage options, either commercially available or being researched. And we want to be up in this upper right-hand corner. We do have a couple of things there. We've got pumped hydro. That is taking a site that has a very large elevation change and having an area on the upper side where we could impound water, and an area down below where we could store water. We could use renewable energy, hopefully, to pump that water up that hill when we have renewables, and then bring it down through a conventional water turbine like a hydro station when we need the electricity on the grid, when we need it most. That's on the scale of hundreds of megawatts for multiple hours. Everything else, the other thing there, compressed air energy storage. We got a couple people that saw those slides tonight. The idea is using renewables to pump or compress air and store it in an underground containment like a limestone cave or a salt dome. and then use that pressurized air on the front end of a conventional gas turbine, and we raise the generating efficiency of a gas turbine from about 42% up near 70%. But again, we're still burning fossil fuels, natural gas, to produce electricity, but at a much more efficient level. And again, renewables supplying some of that stored energy. Otherwise, nothing else is up in that upper right corner, although Elon Musk just delivered last year about 100 megawatts of battery to Australia to prop up some weak areas of their grid where they have a high amount of renewable energy on the grid and trouble keeping the grid intact when the sun doesn't shine or the wind doesn't blow for a long time. And by all accounts, that's working out pretty well. That's been a pretty good operating year for Elon Musk's, I believe that was a 100 megawatt installation, as I recall. But that's pushing this line out to here, but I think in the area of minutes as opposed to hours. But there is no silver bullet. And for me, it all comes back to the sun. If we draw a circle around the Earth and we think about what makes energy in the Earth, there is some radioactive materials naturally occurring in the Earth. They're decaying. There's some latent energy there that's raising the temperature very slightly on Earth. In addition, Earth's rotation around the sun and this coupling with the moon create tidal forces that produce gravitational heat. Again, not a whole lot. We're constantly being bombarded by radiation from space. Again, not much of a harnessable energy source. And really, everything else, whether we're talking about coal, oil, natural gas, wind, solar, that is all solar driven. Oil, coal, fossil fuels, that's just stored sunlight. That's thousands of years of stored sunlight driven into the earth, compressed and baked for tens of thousands or millions of years to make this very dense, very energy dense fuel, but it's just petrified sunlight. So when we look at the solar potential, we said we are using 14 quad per year of electricity in the U.S., 100 quad of all energy sources. Every year in the lower 48 states, 32,000 quad of sunlight hits the lower 48. The potential is there. This is the only solution that's sustainable. We've, benefiting from the sun has been going on for 4 billion years. And it's worked out pretty well. It's only in the last 100 years or so that we've lost sight of that. So it's up to you to figure out how to make that something that continues on for the foreseeable future as a way to keep moving forward sustainably. So my question for you is, do you even worship the sun? So as an engineer, my experience as an engineer, these are some important things that I have found. Engineers that I respect do these things. First of all, they're ethical. And if you can't look at yourself every morning and say, you, I like you, you're not doing it right. Okay? The other thing that I really admire about good engineers is they're curious. They often say, I wonder how that works. And then they go and find out. And it improves their knowledge. And it may be something very far from their expertise. But you'd be surprised every time you learn something new in a different field, how it can come back and inform what you're doing in your field. So always indulge your curiosity. Also be humble. Nobody likes an arrogant engineer. Even though you're right, you know, I mean, let's face it, you're the smartest person in the room. But people don't like to have that rubbed in their face. And treat everybody with respect. You know, you'd be surprised what you could learn from the person that cleans your office. Of course, we're trained primarily as problem solvers. But one thing that comes from that is quickly identifying a problem. And if you're in a corporate environment as an engineer, you are surrounded by inefficiency. You are surrounded by historical practice that makes absolutely no sense. Do not ever be the person that identifies problems time after time, unless you also have a workable solution to suggest. All right? Don't be known as the complainer. Be known as the one actively trying to make things better with solutions, not problems. And something that we certainly don't teach over in electrical engineering, but be prepared to defend your work. There's no reason why your idea should be given the time of day, or there's no reason to think that a young engineer has the best solution. Document it. Be prepared to defend it. Be prepared to fight for what you've worked on, because nobody else will. And engineering isn't about taking somebody's word for it. It's about having the documentation, the calculations, the simulations, the sensitivity studies to back you up. And God forbid you design something, and let's face it, nothing can be designed idiot-proof. All right? If you've ever, this happens all the time in electrical engineering. A student builds something and gets it working, and they say, hey, look what I did, look at what this does. And whoever they show it to touched the one thing, their finger is drawn by some cosmic force to the very most vulnerable spot in that whole circuit. And they say, what happens here? And then there's smoke and it doesn't work anymore. You can't engineer away, you can't make things idiot-proof. And God forbid some idiot kills themselves on your work. And you'll have to ask yourself, was that a day that I was, being ethical and diligent, and I did my utmost to design that safely? Or was that a day I wasn't feeling great and I phoned it in and I took somebody else's work and took 15 minutes and shaved some rust on it and passed it on? So make sure you document everything you do. Engineering is very repetitive sometimes. And be always of the mind, anytime you get a new project, to do it right. Do the research. Learn every aspect about that project you can. Get it right the first time. And then put it away, because it'll come back. And you'll be ready the next time. You'll have a really easy time brushing off that design and reusing it than having to say, oh God, I knew nothing when I did that. It was horrible. I'll have to start from scratch. And ultimately, you are your best tool. Be willing to talk with management about investing in your continuing education, and even on your own with the internet. It's so easy today to try to continue to improve your knowledge base and skill set. Learn new things. Challenge yourself. The one thing that engineering education should teach you is that you can learn hard things. The other thing engineering education should do is give you a critical mass of tools with which to continue to teach yourself new hard things. And do it. You won't regret it. That's all I got. Any questions? Any comments? Yes?
How do you feel about nuclear fusion?
Love it. No, so the thing about nuclear fusion is that in the 50s, the Russians came up with the tokamak as a containment vessel, a toroidal vessel for containing fusion processes. And the world said, oh, fusion is 10 to 20 years away. Then in the 60s, they developed some laser ignitions, or maybe it was the 70s. And the world said, oh, fusion, 10 to 20 years away. Now, in about 2010, 2015, somewhere in there, the Europeans came up with the Stellarator. And that's a tokamak on acid. The containment vessel twists just as the way they know that no matter how you balance the magnetic containment forces, that plasma that you want to circulate in the toroid is going to twist on itself. And so they did fine calculations, and they actually made the toroid twist where the plasma should want to go. And now, so fusion's 10 to 20 years away now. We'll see. That would be great. Don't count on it. Maybe we really don't know how the sun works. I don't know. Any other questions? Well, that is my time. Thank you very much for listening.